This is 10.6, and it is solutions to the percent error FIP quiz. Percent error is the accepted value minus the experimental value divided by the experimental value times 100. So fairly simple. And on a test, I want to tell you, you get a point for writing the equation with no plugins. You get a point for listing variables, you get a point for writing the equation. So if I were you, I would write that equation, unless you don't care about partial credit because you're such a rock star, and then I would write accepted value, experimental value. So the accepted value here is 64.7 Celsius. My stylus is not working well. And the experimental value, what you observed, is the 63.5 Celsius. So percent error is going to be 64.7 minus 63.5. These are both degrees Celsius. Divided by 64.7 Celsius. I'm going to move this. Times 100 will give us our percent error. So what do we get? I want to show all the steps. The first thing you get here is the 1.2 degrees Celsius. That's how far off the true value you are. Divided by 64.7 degrees Celsius times 100. And what that gets you is 1.8. Your raw answer is, I have a raw answer of 1.854714065%. Always write your raw answer. Reason being, it's mostly a partial credit thing. If you screwed up your rounding or your sig figs in your answer and I can't even tell that you had the right raw answer, I don't give you credit. If I see your raw answer and I know you got the right raw answer and I know that you just screwed up your sig figs and rounding, then you're going to lose like a half a point for sig figs, but you're not going to lose all the points on your answer. So how many sig figs can we have here? 3. Each of our givens had 3 sig figs, so our final answer is going to have 3 sig figs, so this is 1.85% error. And then you circle your final answer. It's 1.85 because that 5 is rounding based on the 4. That's not going to change. Most people did pretty well with this. Why do we do percent error? Because when you look at 64.7 minus and 63.5, oh, I'm not that far off. I'm not that far off. I'm like 1.2 degrees Celsius off. That's not that much. It's true, it's not. And as a percentage of the value, it's not a lot. It's a small percent error. I draw your attention to that because I want to look at the next one and talk about some numbers. On the third one, you got an experimental specific heat of aluminum of 0.156 calories per gram Celsius, but the accepted value is 0.185 calories per gram Celsius. What is your percent error? Same basic setup. We know that percent error is the accepted value minus the experimental value divided by the accepted value, all times 100 to make it into a percent. Kind of running off the edge there. And here we know that our accepted value is 0.185 calories per gram Celsius, and our experimental value is 0.156 calories per gram Celsius. These seem like nonsense numbers, like nonsense units rather. They're not, they're derived. So I've listed my variables, I've written my equation, I'm going to plug everything in. So I have my 0.185 calories per gram Celsius minus 0.156 calories per gram Celsius, the whole mess divided by 0.185, 0.185 minus 0.156, and boy, what a tiny little difference, tiny. 0.029 grams per calorie Celsius as a difference. And that seems so minuscule, it must be a tiny error. I did pretty well. But when you look at that difference in terms of a percentage of the actual value, what you find is that that is what you find is that this is actually a pretty huge percentage. This is a 15% error. Even though it's a small absolute difference, the values are so small that this, as a percentage of those values, is enormous. So you get a 15 point something percent error. How many sig figs can we have? 3. Because each of our givens here have 3, and we have to go with the minimum number of sig figs. So we get 15.7% error. And that's because we're looking at the 6, rounding it based on the next digit, which is a 7. It's gonna move up. Okay? Questions, comments on that one? Like I said, most people who miss this one just miss the sig figs, and that's okay. That's fine. I think maybe a couple people were looking at the rules for addition and subtraction. A word about that. Here's a problem where we have both addition and subtraction and multiplication and division. Which set of rules do we follow? We default to the multiplication and division rules because in the end, they tend to limit us a little bit more. And when you have, as most problems in physics and chemistry are mixed, in most problems you're doing sum of all things. It's very seldom that we have straight up addition or subtraction. And because we don't take sig figs till the very end, if you've got a multi-step problem, you keep your raw answers the whole way through and don't round until the very end. We do default to the rules for multiplication and division. So here, even though you have addition and subtraction, we go with the rules for multiplication and division. Okay, let's look at the first one last because it was the hardest. So basically you have a sample of metal that you believe to be copper. One way to positively identify an unknown sample is using its physical characteristics. Density is a physical characteristic that's easy to measure. So you've got this unknown sample. You can mass density is equal to mass per unit volume, and I'm suspecting that maybe some of you missed this problem because you didn't know that, or you had that backwards. That's one that you should just carve into your brain matter. Density is mass per unit volume. So how much mass something has for how much space it takes up. Copper has a density of 8.96 grams per cubic centimeter, and you can also use the units to figure out that it's mass per unit volume. You find the mass of the sample to be 32.7 grams. Volume of the same sample is 3.741 milliliters. What is your percent error? So this requires you to do two things. You have to calculate the density of the sample and then compare your experimental density to the accepted value for density. So let's do that. Okay, so it is a two-step problem on a test. This would be worth more points than the others because there are 2 steps to it. And again, writing your equation and listing your variables gets you points. If you screw everything else up, but you've given me that breadcrumb trail, I will give you points for those breadcrumbs. Okay, so anyway, as I was saying, writing down your equation and listing your variables gets you some partial credit. If you make a bunch of other mistakes, at least you've got that. So now you have to find the density, 32.7 grams, 3.741 milliliters. We get a density of... Okay, so I get a density, and I also say it again, write down your whole number. Write down your raw answer, 8.740978348. Grams per cubic centimeter. Did anybody notice something funky with the units here? I didn't mean to do it. It was a mistake, but you should be aware of the fact that 1 cubic centimeter is equal to 1 milliliter. They're interchangeable units. So you don't have to go through a conversion to do that. Because, of course, your accepted density is given in grams per cubic centimeter. I gave you a volume in milliliters. Okay, now you have an experimental value for density, and now you're ready to do this. Okay, so I went ahead and plugged my numbers in. You'll notice that I do this little sort of ellipsis. I think that's what it's called, ellipsis. I do 3 dots. That's a visual cue to myself because I don't always want to write down this entire ridiculous number. But the nice thing if you're using the TI-30 multi-views is that you can pull numbers down from above. So when I'm doing chemistry or physics work, I will put down the start of a number and then ... to indicate to myself that there's a larger number and that I need to go back and pull that number down. You actually do need to use the entire number when you do your subtraction. So I actually took 8.96 minus 8.740978348 and used that here, and you can see I've got an ellipsis here indicating to myself that there's a larger number. And I'm just going to use that larger number and divide by the 8.96. Divided by 8.96 times 100, and I get a raw answer of 2.4443808% error. How many sig figs can I have here? 3. Now I did have one measurement up here that had more. I had this volume had 4 sig figs, but my mass had 3. So, and that's a measurement that I took. So my final answer for this is going to be 2.44% error, which isn't terrible. It's okay. It's not great, but we can live with that. Questions, comments, concerns?